Right, good morning. Thanks for staying awake and staying with this lecture course. Fancy new microphone, I feel like some aircraft controller or so. We have a few more problem sessions in the evening. I have my last tutorial this afternoon, but in particular with the problem sessions. If there is anything you were hoping to learn specifically, or if you have a problem where you say, oh, how would one do it with GAP? By all means, feel free to ask me. I'm happy to show in one of the problem sessions some specific approaches to some specific problems if there is interest. So please let me know. So with that, where did we stop last time? We did the orbit stabilizer algorithm to calculate an orbit and stabilizer generators. And we then got the idea that we would use it to decompose a group into a subgroup and cosets. The orbit on the cosets of the subgroup could be obtained with an orbit algorithm and generators for the subgroup with as a stabilizer. And in particular, we could use this for permutation groups where the subgroup itself is a point stabilizer and we get the cosets, therefore, by the orbit algorithm. And by iterating this essentially logarithmizes the size of the problem in that we don't need, that we only need to store the cosets, size of the cosets, and the order of the group is the product of the cosets. So this is the idea behind a data structure which is called a stabilizer chain. So let's assume we have a subgroup of the symmetric group on some domain omega. And the first definition is that of a set of points which is called a base. It's called a base if the only permutations in the group which leave all of these points fixed is the identity. Of course, you could always take all the points, then this result is trivial. But if you have a group which is not the symmetric group, often you can choose much smaller bases. For example, if you imagine you have the dihedral group of order 8, the symmetries of a square, and you let it act on 4 points, which are the corners of the square, once you know where 2 corners go, you know where everything happens. So though you have 4 points, you have only a base of size 2. And in general, actually, it turns out typically you could have a permutation group as long as it's not a symmetric group. In a few other cases, group of degrees several 10,000, and you would have base length maybe 5 or 10. Okay, associated to the base is what we call a stabilizer chain. That's a set of subgroups where we start with a whole group and we stabilize the first base point, and in there we stabilize the next base point. And by this property of the base, this means this ends with a trivial subgroup. So something like that we call the stabilizer chain. And the important property is that if we have a base, any group element is defined uniquely by its base image. If we know what the group element does with the base images, we know what it does overall. If we have the stabilizer chain, if we know the group. I just give you, tell you the numbers of the images of the base points, that is would still require some calculation. So this allows to reduce permutations on a large number of points to some smaller objects, just the base images. Okay, so if we have such a stabilizer chain, how do we store it on the computer? What we store is obviously the base. What are the base points? On each level, we will store generators for all the stabilizers. Okay, I'll tell you later how this thing is actually constructed. It's easier to first assume we have the data structure and see what we can do with it before describing how it is constructed. So we assume for all the stabilizers in the stabilizer chain that we have generating sets for these subgroups. Sometimes people look at the union of all these generators and call this a strong generating set. And this data structure, therefore, sometimes is called a base and strong generating set. and some papers talk about a BSGS, and that's the fancy insider way of talking about a stabilizer chain. Okay, what else are we storing? So, there's my chalk. So, we have the group here. Let's look at an easier example. We have a group, we have a subgroup. The first point stabilizer and the second point stabilizer. And let's assume that is the identity. Okay. What we are also storing are the orbits, and let's just assume the points are 1. Let's assume for simplicity our base would be 1 and 2. What we are storing is the orbits of the base points under the previous groups in the stabilizer chain. So here we have the orbit of the point 1 under the group G, which is also G0. And here we store the orbit of the point, next base point of the point 2 under this point stabilizer G1. And we know this orbit is in bijection to the cosets. And this orbit is in bijection to these cosets. So what we need to store in this data structure is the number for each step. We store an orbit. The orbit can't involve more points than the group is acting on. And if we have m steps, we therefore have about m in magnitude m times order of m times size of omega many things to store. And we will see that that is much less than the size of the group. Okay, so what can we do with such a data structure? We can calculate the group order, because the group order is the number of cosets times the number of cosets times the number of cosets, because we end up with a trivial subgroup. We can also test whether an element is in the group. How do we do this? Let's say I come with an element X and I ask, does it lie in the group? I look at the image of the point 1 under that element. Well, if that image does not lie in the orbit, clearly the element can't be in the group, right? That's the definition of the orbit. So if the image is not in there, I can say element is not in there, I can discard it. If the image is in there, I have the orbit and I also store the transversal, so I have an element in the group G which maps 1 to that same image. I'll divide it off. And once I divide it off, I will have an element which fixes the point 1. Okay. But if the element I start with is in the group and I divide off this element in the group, the quotient is in the group. So I have to reduce the question of my initial element being in the group to the question of the quotient being in the next group in the stabilizer chain. And now I can iterate this process. And at some point it ends and I have the trivial subgroup, and I can clearly, easily check whether an element is in the trivial subgroup or not. So that gives me a membership test in the group. So with the stabilizer chain, it gives me the group order, it gives me a membership test, and it even gives me, that is not horribly hard to think about conceptually, it's a bit tricky to program. If you remember how the transversal elements were obtained as products in group generators, if you trace this through, you basically can express your element as a, I think I actually have this on the next slide. Yeah, sorry, let me put the slide on. So, what else do we have? We have a bijection between the group and the possible tuples of base images, because the group order is the product of the number of cosets. The cosets correspond to the orbits, which are the possible base images. So the tuples of all possible base images correspond to the group. So the group, which is an object initially difficult to describe, now basically is described by some cube in n dimensions, right? Where each dimension is one of the possible orbits. So I can enumerate the elements of the group, enumerate even in the sense of compute a bijection between the group and the set of numbers 1 to the order of the group. I can say, I want the 7 millionth element in the group, or here is a group element, give me its number. And I can use this, for example, for effective storage, because in general, numbers take less space to store than permutations on a lot of points. I can write every group element as a product of transversal elements. That's what the membership effectively does, right? It takes the group elements, divides off a transversal element, divides off a transversal element until we end up with the identity. We can just bring the product of the transversal elements over to the other side, and we have the element expressed as a product of transversal elements. If we remember how the transversal elements were obtained as products in the strong generators, that means we can write every element as a product of strong generators. And if we furthermore remember how the strong generators were obtained as words in the group generators, basically that is just tracking through how elements are and keeping track of how elements are generated. I can write every group element as word in the generators. Caveat, often this produces very long words. But that is basically something which one can use to work with homomorphisms given on generators. Finally, I can choose what base I want. Here I've chosen the base 1, 2, but I could choose another base. In general, a group has many different bases. Not all the bases have the same, not all irredundant bases have the same size, but there are many of them. And if I want to find the stabilizer of a particular point tuple or find elements which map point tuple in a particular way, I could choose that point tuple to be my base or be part of my base, and then I can immediately read off such elements. Okay, so how do we get such a stabilizer chain? The algorithm for it is called the Schreier-Sims algorithm. Schreier, because it uses Schreier generators, which are named in honor of Otto Schreier. Sims, because the algorithm was invented by Charles Sims in about, well, actually a little bit before 1970. So, I mentioned already last time that the difficulty is often that we get a large number of Schreier generators. And if we calculate this stabilizer chain naively by saying, calculate the orbit of the point, take all the Schreier generators and make them as generators for the stabilizer, we end up with an awfully large number of generators here. And by iterating it, we are iterating awfulness on awfulness and would end up with tons of generators in lower steps, which would make it completely infeasible. So, Sims' idea is to say, let's work with a partial data structure. Let's assume we have already some data structure like this, but it's not yet complete. And what we're doing is, each time we are getting a new Schreier generator, let's take the partial data structure and let's run that membership test for the Schreier generator on the partial data structure. If the membership test says yes, well, then I have expressed that element as a product of the things I have already here. That means that Schreier generator is redundant. If it says no, either the Schreier generator is really not redundant or my data structure is not complete. So then I recurse to the subgroup here and add a new generator. So the basic operation is that we have some subgroup in this chain. We have an element which we pass to this subgroup. And what we do is we start the membership test by looking at the base point image. And what will happen is either the base point image lies already in the orbit. So that's the first step of the membership test. It lies in there. Then I divide off the transversal element and have a new element I put in the next lower level. And I iterate this Either it iterates through, then I have a successful membership test, or it fails on some level, and then it will fail on that level by an image not lying in the orbit so far. And that means I need to add the generator and I need to extend the orbit. What could also happen is if I go through on the bottom, that my chain is not yet long enough, that I need to pick further base points and make the chain longer in number of steps. And that's what calculates the stabilizer chain. This is not a good algorithm to think about theoretically. This is something which is much easier to try by hand on small examples. It's also not something where you will need to understand by heart the details of this algorithm to be able to use a stabilizer chain. But I basically just want to emphasize, yes, there is an algorithm which can compute this in an effective way. Some further things we can do with stabilizer chains. We can evaluate homomorphisms. I mentioned already we could divide off elements, but a fancier way is actually to say if we have a homomorphism from a group G to the group H, we can embed into we take a direct product G cross H and represent the homomorphism by a subgroup, the subgroup of the pairs G, H, where H is the image of G. That is a subgroup of the direct product. Now we build this subgroup, of course, is isomorphic to G. Abstractly, it's just G. But because it has in the second component the H part, we could build a stabilizer chain for you using only the points on which G acts. And if we decompose now pairs using only the G part, using the stabilizer chain, we basically, the remainder we are getting is, well, the inverse of the image because it's the inverse of the H part. So we can use this to evaluate arbitrary homomorphisms. We can also find kernels and defining relators. So if we have such a homomorphism, we can, if we have a homomorphism, look at this subgroup, we can, again, we form a stabilizer chain. If we are sifting through elements through this chain till the G part is trivial, we get generators for the kernel of phi. And if we do this for H being a free group, actually we will get a presentation for G, but that's something we'll do later. But so homomorphisms also can be worked with using stabilizer chains. So far I've talked about permutation groups, but basically every finite group could be interpreted as a permutation group on a suitable domain. Matrix group acting on vectors, or in the most pathetic group case, a group acting on its own elements by right multiplication. So we can do the same thing there. We can say, build a stabilizer chain for this group for some other action. And we can thereby work with matrix groups, with groups of automorphisms or so. In fact, we don't need to use the same action on every level. We could, here we are always acting on points, but one could choose different actions. If you have a matrix group, you could first act projectively and only later you act on vectors, thereby making the orbits shorter. But in general, as I mentioned already last time, orbit length can be very large. If you go take matrix groups, if you take the full linear group, your vector orbit length get very quickly so huge that, and that is in some examples unavoidable because groups don't have subgroups of small index. So this approach of using stabilizer chains for other groups, it's something which works well in certain cases. It's useful for matrix groups for some base cases, but it is not a one-for-all solution which will be able to work with arbitrary groups efficiently. Okay, so what we have done is, for permutation groups, order permutation group given by element, by generating elements. We can calculate the order, we can test membership, we can evaluate homomorphisms. But there are more things which one might want to do. You might want to find elements with certain properties, subgroups of all elements of certain properties if they form a subgroup, say the centralizer of an element, the normalizer of a subgroup, an element which conjugates one subgroup somewhere else, intersection of two subgroups. How is this done? This is done by something which is called a backtrack algorithm. And I will just briefly talk about the idea of that backtrack algorithm, but I will not go into details how the backtrack is done. So what does backtrack mean? Well, it means walking backwards. It's basically the idea if you have a labyrinth and you want to find the way through a labyrinth. What do? You go some way, at some point you end up at a wall, you go back to your last fork, you go the next way, and so forth. Or more computer sciencey, you traverse a tree. You traverse a tree by going by a depth-first approach, going through all the leaves and then going back, and so on. Well, a stabilizer chain basically gives us a nice way to represent a group as a tree. The first level of the tree are the images of the first base point. The next level of the tree are the images of the next base point, and so on. And if we take the corresponding transversal elements, we could, by multiplying the transversal elements along the edges, we would get all elements of the group on the bottom level. And this is, I think, A4, what I've done, what I've taken here as an example. So we get a tree where the leaves are all the group elements, and by going through, I can construct all the group elements. So I can run through the group by running through this tree and thereby use standard computer science techniques for running through to look at all elements. And if I want elements with a particular property, I can do that and collect the elements on the way. So I can find elements which centralize, normalize, lie in an intersection, and so on. Well, if I just do this naively, of course, I'm running through all group elements, and if my group has order 10 to the 20, this will never terminate in my lifetime. So what is necessary to make this efficient, and that's where I will be rather vague about the technical details because that gets messy very quickly, is we will not just need this process of running through, but what is crucially needed is a process what is called pruning the tree. Based on decisions we have found before, we might want to prune some of these branches that we don't need to run through all of them. And the case where this is easiest to understand is, let's say I want to find a permutation which conjugates the permutation 1, 2, 3 to the permutation. So I want some permutation alpha which conjugates this to, let's say, 4, 5, 6. Well, if I run through the tree, let's say I first look mapping 1. What I actually know is, in this case, 1 needs to be mapped to 4, 5, or 6. If 1 is mapped to 7, the permutation is completely useless, right? So all the branches which do not map 1 to 4, 5, or 6, I can cut off. I don't need to go through there. They will be useless in every case. Next, if I know where 1 is mapped, let's say 1 is mapped to 5 by a permutation, where does 2 needs to be mapped? 2 needs to be mapped, well, certainly to 4, 5, and 6, but even more. Once I know where 1 is, if 1 is mapped to 5, 2 must be mapped to 6, right? So on the next level, if I look at where 2 is mapped, once I know where 1 is mapped, I know where 2 has to be mapped, and I again can cut far more branches. And thereby, so that's basically, in a very toy example, the idea what this cutting of branches means. And that's, in the end, what is needed to make this algorithm effective. As I said, it's used by GAP for centralizer, normalizer, set stabilizer, intersection. Yeah, so these are some of the routines where it uses. There is two generic functions, element property and subgroup property, which would use a backtrack search. You could specify your own function and search for elements with a particular property or a subgroup consisting of all elements with a particular property if that property defines a subgroup. Okay, very good. So far, everything seems to be hunky-dory for permutation groups. But there is a problem lurking in the background which we push to the side. If we look at the Schreier-Sims algorithm, it's a deterministic algorithm. It is polynomial time in the degree of the group. The exponent is a little bit large. If the way I described the algorithm naively is n to the 7, and some people claim that it's not an algorithm anymore because anything which is worse than n cubed will not work on any larger example. If we use the Schreier tree more cleverly, we can get down to order n cubed. But n cubed still can be large. If we have n not completely small, let's say n is a bit larger than 1,000, then n cubed is already pretty large. So even n cubed is not good enough. And why do we have this problem? The problem is basically that we have all these Schreier generators which come in and which we are still processing. A lot of them will turn out to be redundant. A lot of them are thrown away, but I still need to handle them all. And just by this handling, that's what slows down the algorithm. Instead, what one would like is what is called a linear time algorithm, nearly linear time algorithm. We allow some logarithm of n as well together with n, but that's what people aim for. And in fact, this seems to be, well, not yet completely in grasp, but there is only one obstacle left for proving this. If the group has a short base, so if it's not the case of the symmetric group or so, but we have, or some of its relatives. And how can one do this? Well, if you don't require a correct result, to start slightly flippantly, it's very easy to get a result quickly, right? If you don't require, if you give me a difficult calculation, or you don't require me to give you the correct answer, I can come up with an answer very, very quickly. So, what can we do? Let's not use all Schreier generators, but just some Schreier generators, or actually, what one would do is to use some random subproducts because they behave stochastically a bit better. What will happen is, if we just take some of them and we throw others away, the data structure will not necessarily be correct. It will have mistakes. But if it has mistakes, it will end up in a data structure which is too small because we are missing things. So the product of the orbit lengths will be smaller than the group order. So we can detect this if we know the group order. That's why if you have a permutation group of larger degree and larger order, if you know the order and you tell GAP what the order is, the initial calculation is much faster because it does exactly this. It does this random-based calculation where it just hopes that things turn out well. And most often they do, and it can say, yes, because I know the order, I have a verification, I have a certificate that things have gone well. One can actually do an error analysis of this and describe quite well what the error probability is. And in the end, however, we want correct results, and there are basically two things which can be done. One is a combinatorial verification, which is due to Sims. In the textbook by Akos Sheresh on permutation group algorithms, there is a description. And that's what GAP currently mainly uses. The other thing, and that's something which is both for some aspects of gap in the future, but also in the future for some talks next time. I think this will be tomorrow's talk. One can actually start taking the stabilizer chain and get a presentation from it and use that presentation to verify things, but that will come later. Okay. At this point, I want to leave the permutation groups for a little while aside, and in part because we have the tutorial, second tutorial about permutation groups this afternoon, start talking a bit about finitely presented groups. So, what is a finitely presented group? A free group is words over I want a finite alphabet. We take relators. Well, I will interpret a relation A equal B as A divided by B to have a single element. It's a finite subset of the free group. And what I will write this way shall be the quotient, free group modulo the normal subgroup generated by these relators. That's what I call a finitely presented group. Some people are a bit picky in that they distinguish this thing which they call a presentation from this thing which is the finitely presented group. So they can talk about different presentations for the same group. I will take the freedom to be sloppy here. So let's start with an easy example. What is basically, at least in all the textbooks I've seen, the first example of a non-abelian group. The dihedral group of order 8. Generated by two elements, R and S. R for rotation of the square. Reflection in a square also starts with R, so we don't call it R, but we call it S. And if we speak German, we can say it stands for Spiegelung, and thereby have the letters still fit nicely. Right? We have the rotation, 90-degree rotation. We have some reflection. They together generate the group. And they satisfy the fact the rotation has order 4, the reflection has order 2, and rotation times reflection is reflection times rotation inverse. And I think this is with some, modulo some different writing, essentially the example Heiko gave already earlier. And what then the argument in the textbook is we can get a normal form. So this group has at most 8 elements. One could show by looking at the actions on the square that there are indeed 8 different elements. So we have exactly 8 elements. The normal form helped us to bound the group order. Images, ways how the group can act, shows us that we indeed get that many different elements. Can we do so in general? And we are clearly not the first one to ask that question. This was first formally formulated by Max Dehn in 1911, and they are called Dehn's problems. If we have a finitely presented group, can we test algorithmically? Well, he didn't know the word algorithm in the context we use it now, so he was talking a little bit around, but if he had known the word, he would have said algorithmically. Okay. If we have a word in generator, does it represent the identity? Are 2 words representing conjugate elements? Can we test groups for isomorphism? These are things which one clearly would be interested in. And people looked at this, and then there came as a initially somewhat dampener, a famous result in 1957, proven twice independently by an American William Boone and by a Russian Pyotr Novikov. They say, no, you cannot. So what they're saying is there cannot be an algorithm. Not your algorithm is not good enough, but they say there cannot be a general algorithm. How does this happen? Well, now we would need to be more specific. What does it need to be an algorithm? Take the model of a Turing machine. Essentially, they reduce the Halteproblem, the problem whether a Turing machine will stop. The basic result is there cannot be a universal Turing machine which will test whether other Turing machine stops. And what they do is they recode a Turing machine in form of a presentation. where the Turing machine will stop if and only if the presentation represents the trivial group. And since you can't decide whether the Turing machine will stop, you cannot test whether a presentation represents the trivial group. So this means anything we do with a finitely presented group on some level is heuristic. If we end up with a result, that's great. But we cannot expect that in every case an algorithm would find an answer. And that is guiding GEP to be slightly more careful when working with finitely presented groups. For example, if you take a finitely presented group, and some of you tried that yesterday, you ask for the centralizer of an element. GEP will say, I can't do so. Why not? Because it might not know that something would run in an infinite loop. In this case, tell, if you know the group is finite, tell GEP that the group is finite, or ask for the size of the group. Once this is done, GEP will actually do a potentially hard calculation, find that the group is finite, and after that, the centralizer calculation will work. Okay, so let's look at some examples of creating finitely presented groups in GEP. We take a free group and we can give the number of generators, or we can specify the names of the generators. Relators is just a list of elements in the free group. There is a convenience function, parse relators, which allows you to write the presentation in a short form, as it often is given in papers. We take the quotient. The quotient is the finitely presented group. These elements in the finitely presented group are printed in the same way as the elements in the free group, but they're different elements. So there is a function if elements group generators are given by symbols, one can assign generator variables, will assign these generators to variable names. So the variable A will be the generator A of the group G, B will be the generator B of the group G. If I ask, is this generator in F, GEP tells me false. This generator is not in F, but it is in G. So GEP formally, and not just GEP, mathematicians also formally distinguish elements of the finitely presented group and elements of the free group, though they're printed the same way. This continues if we go to arithmetic and element equality. When we multiply elements, initially elements multiply like elements of the free group. In that group, if I multiply A times B times A times B, it tells me it's AB squared. If I ask for the order of it, it is the identity. Indeed, if I compare, it says it is the identity. So equality tests work as one would expect, but the elements are still represented as products. So what one can do, and that is something one shouldn't do in huge examples, but what one can do in small examples to print things nicer is, and that's what we have here on the right-hand side, we can force in a finitely present, let me mention first, as soon as we are doing something like asking for the order or doing an equality test, there is a calculation in the background. You will often see this, that GEP, you ask this the first time for a particular group, it will take a little time. This triggers a potentially highly non-trivial calculation, namely, we are calculating, for example, a faithful permutation representation or something which is called a confluent rewriting system, that is basically a generalization of the idea of a PC presentation and collection to give us a normal form, to do this equality test, to be able to check are elements the same. What you can also do by calling set reduced multiplication G, and there you don't type true, have the argument true because you wouldn't really call it with false. Once you do this, all products which are formed afterwards are implicitly reduced. So that is a convenience function which makes it nice to work with this group. The problem is it comes at the cost that Once you do the first arithmetic here, then it actually will need to calculate a confluent rewriting system, which in the worst case is something like working out the full multiplication table. So that can take some time, but for small groups, and if you want nice ways to represent elements, that's the way to go. Yeah, what can we do with free groups? So I said, testing whether they're trivial is hard. There is one thing we can do easily with a finitely presented group. Namely, if we have a finitely presented group, a map given on the generators is a homomorphism if and only if the generator images satisfy the relators. As I learned 2 days ago, this is apparently Van Dijk's theorem. And the proof is basically that you use the fact that on a free group, any map is a homomorphism. So, a main tool for working with finitely presented group is to work with homomorphic images. They will never give you, are not always guaranteed, or you need to do extra work to have a guarantee that they give you the whole group. But there are things which you can do. And there are some algorithms, for example, there is the p-quotient algorithm which Heiko is talking about. There is a more basic version, just an abelian quotient. In GEP, there is a function, maximal abelian quotient. This gives you the quotient which is the largest abelian group. Or if you just want the structure of the abelian group, there is a function, abelian invariance. Two further versions which I like to think of as quotient algorithms. One is what I call a G-quotient algorithm, and of course the way I described it, I should have called it an H-quotient algorithm. If we have a finitely presented group G and a finite group H, I can try to find all homomorphisms from G to H by simply saying if G has 3 generators, I run through all 3 tuples of elements of H and check whether the map of the G generators to this 3 tuple will give me a homomorphism. I can test that. So, what if I want that the quotient actually is H and not a subgroup of H, I might want that the map is also onto, so that these images generate the whole group. And one can do that by running through these tuples only up to conjugacy, and I'll tell you in the last lecture how one can do that. One could do this reasonably efficiently and thereby find all images of a particular isomorphism type. As a variant, what one can do is we could say H is a symmetric group of some moderate degree, and we don't require onto, we just want that it's a transitive subgroup, and we can thereby find all subgroups of index up to n, because the action on the cosets of a subgroup of index n will give me an S image, a subgroup of Sn. And that is called the low index algorithm. The implementation is a little bit different, but that's the basic idea of the algorithm. So let's look at this in some example. And the examples I have here, these are actually not just willy-nilly random presentations, but these are presentations which go back to the book of Coxeter and Moser, and which have driven quite a bit of investigation, these types of presentation investigations of the groups and development of algorithms. So, for example, I could take, let's first do an easy example, this group generated by 2 elements, this presentation. I ask GEP for the size of the group, and it tells me 23,000 and a little bit. Okay, now I'm just changing the 6 to a 10. And I ask it, and I let it run a while, and run a while, and run a while, and at some point I'm fed up, and I press Ctrl-C and interrupt and get out of the break loop because it doesn't do anything, and I don't see where it's going. And that's often the behavior when working with finitely presented groups. You do some calculation, it doesn't terminate, and you have, because of the Boole-Novikov result, you have no idea, is it because you're not patient enough? Is it because it can't do it? Is it because the thing is so enormously huge that you have no chance to get the result there? So, if we take this group G here, I ask for the abelian invariance. That's the structure of the quotient G modulo G prime as a direct product of cyclic groups. In this case, it's just cyclic of order 2. I calculate the subgroups of low index. When you do this, I would probably do this in steps. Start with a small index like 5. If that terminates quickly, go to 10, 50, and so forth. Very rarely, only if the presentations are very, very small, are you able to go beyond 40, 50. So the low index algorithm on its own is not able to find subgroups of larger indices. Yeah, so it gives me a list of subgroups. For the moment, it doesn't yet calculate generators for the subgroups because it doesn't need them. Yeah, and we have find subgroups for these indices. What I've done here in this example, I asked for the abelian invariance of all these subgroups. So for example, this subgroup has S modulo S prime cyclic of order 2. Here S modulo S prime is C2 cross C2 cross C2. And here suddenly I get a 0. The 0 means Z. So I have here a subgroup S that S modulo S prime is isomorphic to Z cross C2. That means this subgroup is infinite. That means the group is infinite. So indeed, I wouldn't have, this algorithm would never terminate. You can argue it's not an algorithm, it's just a process, but yeah. So that's some example. Let's take another one. Here, this is another presentation. This is a rather notorious case of one of these Coxeter-Moser groups, G3719, 3 generators, these relations. And what I want to illustrate here is the G-quotient algorithm and another function which can be useful, the simple groups iterator. This will get me an object where I can iterate through all simple groups by increasing order. So I have this object that I call next iterator of the object, which gives me the next smallest simple group. The parameters of simple groups iterator actually could be, I could give a starting order, and I can give as an option, options are use the colon notation. I could give the option no PSL2, that it will skip all the PSL2s because there are just so many of them and often they are not interesting. So what I'm doing here is I'm running through simple groups by increasing size. I print what is the group, which will print some name which it has stored. I ask for the quotients of that isomorphism type, all of them each time I get a list until I get a list of length greater than 0, so that there are actually some. So it starts with A5, PSL 27, and so on. It runs through some, and at some point it finds the Janko group J1. Okay, there is one quotient of that group, which is the Janko group J1. I can ask for the kernel of that homomorphism and I get some subgroup. I can also ask what is the index of this subgroup. That's of course the order of Janko 1. So what GEP is doing there is actually something very slightly clever in being able to represent subgroups of quite large index. And it can actually, we'll see soon, even larger indices. If I continue running this, so at this point I continue with the same kind of commands, it iterates further, and at some point it finds PSL 213. And that's basically the only 2 quotients which are known for this group. At this point, it's not known whether this group is just the direct product of these 2 or whether it is larger. So we have these 2 subgroups. Yeah, I mentioned PSL2 business. Yeah, and I think that is well, let me briefly continue in the example what you can do furthermore, but I'll tell you next time how this is actually done. We can take these 2 kernels, we can take the intersection of the kernels and get a subgroup of a really large index. that is not stored for those who know already what coset tables are. This cannot be stored with a coset table. And in fact, it's stored via a homomorphism, and I can use that homomorphism to go to the image, which is a huge permutation group. I can calculate in the permutation group, get subgroups of the permutation group, say some maximal subgroup of the permutation group, pull it back in the finitely presented group, and thereby find maximal subgroups of a finitely presented group which have huge index, which the low index algorithm would never find. Yeah, but I am out of time here, so thank you very much, and I'll see you later.